Right, this is 3.8, all about inverse matrices. We will be able to find the inverse of a 2 by 2 matrix and write and solve matrix equations for a system of equations. Right? So recall, what do inverses do? Like, what is an inverse in general? When we think about addition, all right, so when we think about addition, the inverse of addition is subtraction, all right? And so the inverse of 1 in the addition case, the inverse of 1 is -1, because when they are added together, they equal 0, right? 0 equals the additive identity. With multiplication, the inverse of something like 1/3 is 3, because when they multiply together, they give us 1. 1 is the multiplicative identity, all right? So when you think about what inverses do, a couple ways we could think about this. They undo each other. They undo each other, or they give us the identity. Give us the identity, all right? The identity, that's a math word that's going to be important here in this section, okay? So there's an identity matrix, all right? This is where we're headed. So big idea, big picture, a matrix times its inverse will equal the identity matrix, right? The notation here we see is there's a little -1, kind of like an exponent. So matrix A times its inverse equals the identity matrix. And this uppercase I is what we use to denote the identity matrix. And the identity matrix, it's an n by n matrix, so it's a square matrix, and it has ones all along the main diagonal, from the top left all the way down through the diagonal, all the way down to the bottom right. So if we had a 4 by 4 matrix, 5 by 5, 6 by 6, whatever, we would see ones all along that main diagonal, and then there are zeros everywhere else, okay? And so for most of these, we're really just going to be working with 2 by 2s, all right? And so what that means is that we have 1, 1 along its diagonal, and then 0, 0. This is called the main diagonal. I'll write that down, the main diagonal, because for those of you who go on to study math in college, if you take linear algebra, matrices are going to become really, really important. So we're just going to get a little taste of them in this chapter, and that's it. But they may pop up depending on your future, or you may never see them again. Okay, so it just depends on what your path is. So this is the notation for the inverse of a 2 by 2 matrix. Don't freak out. They're actually it's pretty straightforward. The first thing I want to point out, this bar around the A, that's the determinant. All right, so to get the inverse of a matrix A, we're going to take, first we have to figure out what its determinant is. And then we're going to use that as 1 over the determinant. It's going to become a fraction, and that becomes like a scalar multiplier that we're going to then multiply the matrix by. So the inverse matrix, we're going to kind of jumble up some stuff. So if a regular matrix has its elements A, B, C, D like this, we're going to flip the elements on the main diagonal. We're going to flip A and D. They're just going to change places. That's all that's happening. And then B and C, they're going to stay in their place, but we're going to make them the opposite sign. So if it's positive, it's going to become negative. If it's negative, it's going to become positive, right? And this is just kind of like a qualifying statement that the determinant has to exist. It cannot be, it has to be, either in a natural number or its opposite, so it cannot be 0, basically, because we cannot divide by 0 here. So if the determinant is 0, the matrix does not have an inverse, meaning that is singular. Matrix is singular if it does not have a matrix. If it has an inverse, it is non-singular. Vocab that, again, I'm not too concerned about, but if you move on throughout your math career in college, you will see those words pop up again. Okay. Example 1, we're just going to find the inverse here. So first, to find the inverse, we got to find the determinant. So remember from the last section, we want to take the main diagonal, 7 times -3, minus the other diagonal, 5 times -4. All right. And then in this case, it's going to become -21 plus 20, which will give us a determinant of -1. So thinking back to this formula, we're going to take 1 over -1, that's the determinant. That gives us this 1 over the determinant of A piece, and then we're going to start our new bracket for our inverse. Okay, we're going to start our new brackets, and then we're going to flip around these elements. So our main diagonal, they're just going to change spots. So -3 goes up here, 7 goes down here. And then we're just going to change the signs on here. So 5 is going to become -5, and then -4 is going to become +4. And then we will multiply out this scalar multiplier into each element, and we will have our inverse. Right? So 1 over -1 is really just -1. So if we distribute a -1 into each of these elements, we're just kind of changing their signs. So we end up with 3, 5, -4, and -7. That is our matrix. So this means that if we take our original matrix, multiply it times this one, we should get the identity. Okay, so it's a good way to self-check and see, are you getting what you're supposed to be getting. Pause the video, give this one a try. Alright, so hopefully you calculated first the determinant. The determinant, take the main diagonal, -4 times 6 would be -24, minus -5 times 5 is actually going to give us +25. So it's really nice here, this determinant is 1, meaning we don't have to worry about that 1 over 1 piece being the scalar multiplier, because it's not going to change the value of our inverse. Okay, then we're going to flip our 6 and our -4, and then we're going to change the signs of our 5s and -5s. So our final answer is going to become 6, -5, 5, -4. And that is our inverse matrix. All right, so next part of this has to do with systems. So remember way back at the beginning of this unit, I said there were 4 methods for solving systems. So remember, a system is something like x plus y equals 10, 2x plus 3y equals 4, whatever, and you're checking to see where do these intersect. Do they have one solution, no solution, infinitely many solutions? And so we've talked about graphing them. Talked about using substitution and elimination, and I said we were going to come back to matrices. Well, now is the time. Okay, so let's figure out how we can use matrices to help us come up with this type of solution. There's this concept. We can take a system of linear equations and break it into a few matrices. All right, so the system x minus 2y equals 0, 2x minus 3y equals 3. I can break it up so that I take all my coefficients, 1, -2, 2, and -3, and I can make them into what we call a coefficient matrix. All right, and then I can take my variables, x, y, and write them as a variable matrix like this. And then I can set them equal to the constant matrix. All right, so that's a concept, and that's some vocab that's going to have some application. But all this is really saying is, like, okay, if you have your system, take your x coefficients, line them up in a column. Take your y coefficients, line them up in a column. Multiply them x times y, and you would get the constant matrix. All right, and so flipping back to page 18, this is on the very back page of your notes. What this does is it allows us to use this concept, right? The inverse matrix times the constant matrix will equal the variable matrix. So conceptually, say I want to get x and y by itself. I want to get this matrix by itself. In order to move this matrix kind of over to the other side, if you will, I can't just divide. There is no dividing with matrices. I instead have to multiply by the inverse, because that's what's going to kind of allow this to cancel out. Back at the beginning of this video, talked about how inverses cancel each other out, they undo each other. That concept is what's allowing us to do this. All right, so then we can take our inverse matrix, multiply it out front here, and then whatever we do to one side of the equation, we have to do to the other. So we can take our inverse matrix, multiply it out front here, and it's going to equal our variables. That's what this is saying. All right, so it's kind of a confusing concept to wrap our minds around, and there's a lot of spaces to kind of make silly mistakes. So let's work through this one very carefully together. All right, it's asking us to solve this system by completing the following. This is a really popular question on Alex, which is why I'm going through it in the notes. All right, so our system 5x minus 3y equals -6, -6x plus 4y equals 4. Part A says, suppose that the coefficient matrix is the following. All right, so what they did is they took our x coefficients, 5 and -6, and they put them together kind of in a column. All right, and then they took our y coefficients and they put them together in a column. all right? And so we need to find the inverse of this. So we're going to find the inverse of this. Remember, to find the inverse, we have to take 1 over the determinant of A and then multiply it times this stuff flipped around, all right? So first we got to find our determinant. Determinant of matrix A, we want to multiply 20 minus -3 times -6. That would give us a determinant of 2. And then using that information to find our matrix, we're going to take 1 over the determinant, so 1/2, open up our matrix, and we're going to flip around our main diagonal. So our 4 comes up here, 5 goes down here, and we're just going to change the signs of -6 and -3 so that they become positive. And then now we're going to distribute this scalar multiplier. 1/2 times 4 gives us 2. 1/2 times 6 gives us 3. And then we end up with a couple fractions, 3/2 and 5/2. I know fractions are not our favorite, but that's what we're working with. We're not done yet, all right, because it's asking us to write the solution as a product of 2 matrices, all right? So what this is really asking for is this concept here, inverse matrix times a constant matrix equals the variables. So we need to take our constants, which are -6 and 4, and we need to multiply, kind of set up the multiplication. And then this is the equation that we're working with. So this is actually the solution that you want to do for these. For part A, when it's asking you to set up your equation, this is what you're looking for. And then part B is just asking you to solve. All right, so I'm going to see if I can just kind of copy this from one page to the other so that I don't have to rewrite it. All right, there we go. It is there. And so now we're going to do our matrix multiplication. All right, and this is where we got to be super, super careful. Take our row times our column. So 2 times -6 plus 4 times 3/2. And then our bottom row, 3 times -6 plus 4 times 5/2. And we simplify that and we get -6, -8, which is our solution. So what this means is that x is equal to -6, y is equal to -8, meaning that these two lines, this system that we got at the very beginning of the problem, they intersect. The lines intersect at the point -6, -8. We can verify this by looking at Desmos and seeing, okay, here are our 2 equations, and then where do they intersect? They intersect down here at -6, -8. All right, kind of confusing, but that is how you can use matrices to solve systems. That's all I got for you. Take a look at your practice. Let me know what questions you have.